Hello everyone, it's a pleasure to be here. Let me enjoy the moment while adrenaline is flashing through my veins. So I would like to invite you into a journey of creating a model. I will not be focusing on the model itself, since when you see the final model, all you see is actually the glory of the final decisions, the final models, but not all those mistakes, dark side of creating it. And there is always dark side. I know this from experience, and I would like to share it with you. Of course, I will oversimplify everything. Perhaps it will look a little bit better than it is, but I will try to be as honest as possible, and this is my promise to you. Okay, a little bit intro into surrounding. So this is me. I'm revealing myself as a data scientist with all selected facts. If you have any problem with that, would like to challenge, say, oh, you're not right doing that, I am more than welcome after this presentation. If you would like to have geeky discussion, confronting positions, I'm good to have. So, and the most important fact, I have 11 years of professional experience. I have never ever worked with real big data. What's the real big data? But it's not the question. I always was in the modeling side. I was modeling, forecasting, identification, anomaly detection, and something like that. So this is me. And I happen to work in Danske Bank, and Danske Bank is one of the supporters of this event. And Danske Bank is a big bank that hosted in Denmark, but it's considered to be home market all Nordics: Sweden, Norway, Finland, and of course Denmark. There are other countries, and a specific country is Lithuania, because the branch is here closing, but we provide a lot of services for Danske Bank. Huge amount of people. One of them is me, and I'm happy to be with them. So, and what we do in Danske Bank, we do a lot of things, but now I am going to more specific into my project. And this is the illustration of what we do. So here is real estate, real housing, and if you want to go get a loan, you need to go to a bank. And Danske Bank provides a service that is easier than ever to find. So based on the budget of your incomes and your expenses, you can have a map like here that is personalized to you, that green dots indicate the properties that you can expect to buy, to afford to buy, and red ones, they exist, but probably is not for you, not now, at least. And this is not just a nice interface with a bunch of calculations, but it's also an obligation from Danske Bank that you can actually press this button. It's in Danish, so it's a screenshot from our website. You can actually press a button while sitting on your sofa and get real obligation from Danske Bank to give you a money for this particular property. And so you can actually have quite good experience while sitting on a sofa, selecting your house and getting your papers ready to go for the seller to really have a real contract. And this is what we do. So it's real estate domain. And one of the things, it is nice to have some kind of prediction of what this particular property might be worth. What's its price for any living property in Denmark? If you have address, we might say the prediction of this price. And this is what we were building. And this is what I'm going to talk about. Okay, and so this is animated symbolic board of our journey. Here in the center, we see the time steps that we need to go through, and sideways, it is modules of a model, of a pipeline of a model, and that need to be unlocked one by one while we go through the journey. So let's begin. The beginning is always interesting to the data. So what we have public data, the registry of all properties in Denmark. And that includes address, area of living area, basement area, wall material, what's area of the land, do we have a garage, and stuff like that. It's static, slowly changing stuff. We also have something that is list of all contracts that happens during time. In the real contract, that this property was sold by this price and now by this price. And based on this data, we would like to make those predictions. So, and everything starts with KNN. KNN stands for K nearest neighborhood. And it's just a vision that is now unlocking, not unlocking. So if you have property somewhere, and it's not so much use, so we live in neighborhood, the closer the distance, the more relevant it's to us. And we can approximate the price by looking at neighbors. And this unlocks our KNN module, but it's somewhere in the middle, and a lot of stuff needs to be done in order to actually run it. And let's go through our first problem. And the first problem is actually problem of time dimension, that each contract has happened in different time. Time is not important itself, but what is important that in each time it was different bust and boom and cycle period. So price were going up, price were going down, and we need to adjust it somehow. And this unlocks our another model that is time index. We need to adjust according to the time. And by adjust, I mean this kind of illustration that we have general movement. We want to make it flat, but keep the relationship on compared to the average, where the price were higher than expected or lower to expected. And let's find some index. So at the very beginning, we have found something very cheap solution, no model at all, just official statistics, demo statistics. This is property time index. We just take it and apply. By the mean of applying, this is a simple operation, multiply and divide, and actually it's good enough for this moment. It is good enough, but we will come back to this later. For now, we are having this one. Very cheap, very fast. And we run into another problem, and the problem is illustration of how the same houses, but reality is quite different. Those houses are quite different, and sometimes very. And you cannot just average everything and pretend they are equal. And you need to create a model that can adjust that. If you have a garage, that actually might add you plus 5% to a value, or something like that. You can name it. And this unlocks our another module is feature index. So we are doing the same transformation by the features. But here we have more problems. Let's try to adjust it, and let's consider an example. An example goes like this, that we have some nice property with tree in it, and in this close neighbor, we have bigger property with quite similar house. Let's say features are identical, but the land is bigger. Well, once you can expect that the bigger land should cause the bigger price. Does anyone has any objections here? Okay, it needs to be way around. Do you agree that bigger land actually has to cause bigger price? Who's with me? Oh, wonderful. Thanks for support. All you actually wrong. From data science perspective, not data science, actually blind data science perspective, the real thing is the bigger the land, the expectation of a price drops. And the story behind this is like this, that if you have a lot of houses and they are somewhere near that center of Copenhagen, everything around is expensive, including the land, and all lands have tendency to be small as possible, actually. But somewhere outside the river, and it is countryside, where the land is relatively cheap. Since you are already in countryside, why not to have huge land? And those lands have tendency to be huge, but they're relatively cheap compared to center of Copenhagen. And this creates some kind of discrepancy. We expect bigger land cause bigger price, but if you just put everything into a model, you get opposite effect. And this is what you really would like to avoid. The reason those prices are high is not because the land is small, but because we live in the center of city. So what needs to be done here? So it's a problem, and we somehow need to solve it. And what needs to be done is to make sure you have enough features in your data set that is able to extract information that you are somewhere in the middle of a city. And so we were collecting KNN features, we call that way. So we took at your neighbors and look not at the prediction of a price, but on other stuff like minimum distance to your closest neighbor, or something like, let's take some surrounding and count the density of it, how much buildings we have in it, or something like, what's an average area of a land in this particular property, in this particular area. And we are collecting it one by one for each and every household in Denmark. And once you have those features and you put into a model, after that model is able to predict correctly, and at that moment you that supported me, you are becoming right once again. Now we are able to distinguish that those are more important features to distinguish, and this is area land that should increase your price. Okay, let's go further. And since we already dealing with features, we somehow need go back to features engineering, and from original data sets we'd like to make some kind of adjustments. Proportions, something like, but those are individual proportions, and something like what proportion of building you own. If it's in villa, it's 100% yours. If it's an apartment, it's probably 5% yours. All the rest of the building is someone else. Flat apartment is only a part of the building, and this tends to be a very important feature. Okay, and here we go. This is our current pipeline. I will run through once again. So we begin with feature engineering. We calculate all the features. After that, we adjust everything according to our time dimension. Moreover, we're going further, and we collect information about our surrounding, this feature selection. Then we run a model of features. We have a price adjustment for each of one, and finally, we end up having KNN prediction from your surrounding. Yeah, ta-da! We did it. This is zero model that actually able to predict results, give results, and we are quite reasonable. We are happy with that. Is it good enough? Yes, it's reasonably good. Now we have some terminology, what is reasonable and what is good. Well, we were focusing on several metrics, but the most important one is median, absolute percentage error. So we are calculating not kronas, but what percentage we are missed off, and in median, because sometimes it's very heavy-tailed, so we try to focus on central statistics. And I'm not going to present you final number. Sorry for that. It's somewhere between 5 and 15. So it was agreed that I'm not giving specific number, but let's agree to call it 100% at this point. And I will state what our decisions were while talking further relative to this zero model. Okay? And where we are in our time scale, so we are somewhere here. So we already have model, but not even in the middle of this process. So, and now it's time for great question. Great question for any modeler is, and it's an expensive question, by the way, can we do any better? This is a great question, but it's easy question. It's almost always yes, we can. So let's go and try to do something. And the easiest choice is go back to feature engineering. Features, information is all the fuel that runs this model. So let's try to be as accurate as possible. We are going through that, thinking again, rethinking, and doing. Created more features, you need to run through model. Once again, all the models should be calibrated. Hyperparameters, thinking. After that, you have a result. You need to go to analysis phase and look where you were good, where we are bad, and rethink again. And this circle starts over again. Again, you find some features that perhaps you hope it will be useful, you analyze them, and you go to back to feature engineering. And the problem is that this loop does not have inbuilt exit function. It actually runs and runs over and over again. And the moment you can break the cycle is kind manager with a kind question, when are you trying to present your results? And suddenly it breaks down, okay, we're ready, it's good enough. And one lesson learned that this kind of activity is black hole of a time. Whatever a time frame we have, you can spend all of this playing with the data, coming back, analysis. And now it's come time for scary question. Before that, we have great question. Can we do better? Now the question, is it any better? So yes, it is, 2%. You can consider to be good or bad. Well, it's relatively small. You can say, on the other hand, perhaps our initial model was very good. So it's hard to say, and from my experience, you sometimes reach a point when you need to fight for each percentage point of improvement. You can see also this kind of effect in Kaggle competitions. If you compare the board, somewhere in the board you see that 1 percentage point you can drive your way out of the board. So those not so great, but we also have other benefits. And those other benefits like that we were using this model, our code over and over again. It became way more mature. We learn about the data. Now we're ready to take a big hit. And let's make something fancy, something that we can brag about. And this brag about is about our time index. Before that, we just take a cheaper solution, took official statistics, and we are happy about it. It is not optimized according to our problem. It's definitely something we can do about. And so let's do modeling with buzzword, and let's use neural networks. And this is simplified structure of simple neural networks. So we have 7 inputs, and actually they all collide into 3 logical inputs. We're just feeding it, and the prediction we want to say, if we say a location, type, and time, we would like to have a prediction of a price. And we try to fit it. Well, neural networks have tendency to overfit, so we need to make sure it is. We put another layer of regularization, put a noise in inputs, so it's not trained to be this specific location, but somewhere around here. Not specific time, but something around this time. And we use this regularization, and here we go, we have some kind of predictions. And it's, well, very good stuff, you know. Neural networks, everyone is fancy about it. Now we can go to your manager and say, look, we are using neural networks now. Please raise my salary. Okay. And in addition to that, we also have geographical index. Because location is just an assigned effect of this model, and you can also adjust your prices to be a center of Copenhagen or to be in countryside, also to be kind in the same level. Weird stuff. The question is how to decide if model is good. So of course we want to make the best model we have, the best fit, but one very serious condition that out of sample error must be not so roughly equal to in-sample error. So it's general term, but here you need to be very, very strict about it. It's way better to have underestimated model because you are going to track all the other features after that, but you need to make sure it's not overfitting at all because that will create extra noise. And once you are checking about those error rates, I also was investigating graphs. This is a real graph from our working notebooks, that those graphs are for individual properties, and we are investigating if we are relatively smooth, it can actually be as an index. It looks like an index, but for individual property. Okay, now quick question: is it any better? Yes, it's a great victory. It's plus 13%. That actually really improved our model, and we were very happy about it. And one lesson learned: neural networks are awesome. We enjoyed that. Okay, let's go further. Another pile of questions that we have is something like that. Along this whole journey, we are having a lot of questions like what key to use, what radius to use, what aggregation function is the most useful, and stuff like that. So all those parameters were based on our gut feeling of experience, some kind of experimentation, and they never been optimized as a system. But the problem is that since we have a pile of modules, it's quite hard to put everything into one pipeline and say run optimization and we will be happy about it. So we decided to run another approach. We created a U model. U is just a label that stands for unification. Information, uniting all information is possible, and it's using all the features and even KNN predictions as an input and tries to best fit with all available information. And so let machine learning to decide what hyperparameters to use, and this goes like this. If you are struggling to think which aggregation function is more useful, mean or median, you don't need to choose between those. You can actually have both of them and put side by side as your feature columns. Moving forward, if we have k equals 10 or k equals 20, you are struggling to think what is best, you don't need to think much, you can put side by side. And in this approach, if you are very greedy, you might end having blowing your memory because the count of features is multiplying very rapidly. So you need to keep your greed into some kind of level. But now we have a lot of features. You run machine learning algorithms and look of those that are most important and keep only those. If you want, you can have another iteration and run the same function again. And in that way, you can actually choose between hyperparameters that are most important one. And yeah. And now is the question, is it any better? Yes, it's added another 3 percentage points. So we're improving our model, we are happy about it, we are playing with the data, we're modeling, real nice workflow. And where we are here, we are somewhere in the middle. Oh yeah, a lot of stuff needs to be done still. Before going into what's next, we need to answer, is it good enough? Because business already can use this, and we don't need to do anything further. The problem to this question is really we don't know. Somehow we don't know. And the problem is, let's run real out-of-sample prediction, the points where never has been seen by models before, real out-of-sample. Before that, we were using out-of-sample cross-checks, but still all our decisions were made by those points. We're looking at those graphs, and when we try to forecast the real out-of-sample, we bumped into the first problem, the edge of neural networks. So if we have neural networks that creates a chart like that, and our prediction, real out-of-sample, is also always outside the range of a time. It's just by design. And the problem with neural networks that out-of-sample behavior is totally unpredictable. You don't have any control outside the range. And it's kind of problem, but it's not really a big problem. We knew it before. Why it's not really a problem? Because we were using indexes before, and always index is calculated to the past, and you're just using the last known value. So we can apply the same strategy here, just use the last known prediction that is valid, and we might be no better than that. But the real problem is that updating model is tricky, because while you update model with new incoming, you will create all the parameters of your neural network, and that will create changes in the past points. And that's not cool. That's not okay. But the real problem is that the line somewhere in between here, let's say, here, the line is fitted having all available information. That includes from the past and from the future. It's actually smoothing the curve. But at the end, somewhere here, you are only using the past information. So we have real shift bias. And actually, those neural network predictions are kindly overfitted compared to the real world application. And this is the real problem. So this, our great victory, what we were happy about, turns to be a great defeat. We can't use it. Sorry. And lesson learned, neural network sucks. Okay, I should rephrase that because I was bragging about it. It should be used wisely. Okay, so let's go back and try to fix what has been broken. No, not broken, it was never actually working. So let's create a transparent index, and nice solution that does not work for us is nice one piece of code, pandas, group by, average, and that might be it. But it's not working for us since we have some kind of problems. Potentially only few cases might be in that cell. And if you're using that, you might have huge variation in your index, and it's not okay. And we have also time lag. The data is feeding one by one, not as a buckets. Okay, so we need to overcome that. So few observation, and you still need to make some kind of knowledge prediction about that. So this is Tom Bias saves the day. Bayesian statistics nowadays is also used a lot of when you have some kind of knowledge, but not enough observation in some points. So let's try this one. We're not using it directly as from a bottom, but we are using state space framework that uses Bayesian behind it. So this is a simple, relatively simple approach that we make a presumption that our index is composed of 3 elements, and those 3 elements might change independently, and elements by general, municipality, and category. And we will try to optimize this to have the most probable values. And developing machine learning package, we have not found something that was already ready for our problem, so we are developing by our own. And the problem here is something similar that we saw before, that you have code, debug, not necessarily debug. Sometimes you want to make it more abstract to fit other needs as well. The good part here that you don't need a manager to wake up you. You can actually find yourself that now is in a phase that producing results you wanted, and you reach the final stage. And is it good enough? Well, yes. Before that, we have 13%. It turned to be not 13, 11, a little bit lower than neural networks. But now we know it's using only the past information. We can calculate index. We are not changing historical index, all the good stuff we had. So this is good. Lesson learned is that, oh dear, we spend too much time on that. Developing package tends to be at least double the time than you expected. And it's one hand, it's a winning. On the other hand, it's too much effort for that. But now it's working, now it's okay, we're happy about it. Another problem is that we are no geography index anymore, since we dropped out our neural networks. And it's not good because neural networks, well, we are bragging about it, and now it's gone, and we need to replace something. So we took this approach like this, that we took original neural networks, we dropped time index, everything else is okay. Why it's okay? Because geography is not changing, it's almost slowly changing. We are in the same country always. So that's okay, and we come back having pretty much the same pipeline. Okay, and now let's go and try to find some edge cases, and those edge cases is here. We have a country of Denmark. Those are municipalities, as you see. And if we zoom this graph, we might end up having somewhere here, 2 municipalities, and the property is somewhere between them, at the very edge of municipalities. And the problem arises that at the very edge, you might face some kind of miscontinuity of index. Each index is calculated for municipality, so they might change slightly. And it's also not okay. So what we are seeking for is to make some kind of smoothness here. And let's use weighted average. It's very good for smoothing. We have 2 points, you can actually always smooth. But the problem where to get weights. And here unlocks one of the tops. So let's calculate the weights based on the geography on being close to the edge. And we have tried several approaches. The easy one, distance from the center, never worked. The shape of something else. So we tried clustering techniques. So we put municipalities, we put here. So run machine learning algorithms to learn clustering and prediction to be in one cluster or another might be real weights for calculations. This might work, but it creates another edge cases, and we try to avoid that as well. And the easiest solution actually is not to apply any model. Easy and simple, calculate the proportion of your neighbors. And that actually is something that worked pretty well. My illustration is that if you have something at the edge, you drive a circle around it, calculate on one side properties and another side properties. So in this example, it would be 3 to 1, 3 to 2 compare. Those are weights, and that's good enough. Okay, where we are. We are somewhere here. We can actually see the finish line, but still not yet. We are able to make results. We fixed what was broken. And now here goes another kind of question. Imagine you have a property somewhere, nice property, and you have prediction for this particular property. This. Can you trust this result? Not on average, not on general performance, but this one. And in matter of fact, you can. For this particular case, it's somewhere in the blocks of very similar houses. It is quite good houses. There are a lot of contracts going on back and forth, and you're pretty sure plus minus 5% that this is the price he's getting for. You can something to procure, it's easy. But the question is, can we know in general for any house, can we trust it? And this unlocks our another model that is quality score model for each and every house. And it goes like this, that let's define what is quality, what is good. So we are defined it the probability of hitting some kind of interval. That you, this is the prediction, this is the interval, what's the probability that we are going to hit it. And the approach we're doing is, well, simple enough. We created an indicator that says you are hit it, interval, you are missed it, 0, 1, classical approach in data science. Run a machine learning engine. Actually, it doesn't matter which one. We have tried several of those. They work pretty much similar. All the stuff you need is information. And here you go, we have a prediction of this probability. And this is our quality score model. And the question, can we do any better? Yes, we can. And by yes, we can, we need to go back to KNN features calculations. Before that, we are focusing on having the best possible predictions. Now we're collecting information to have quality score. So, for example, standard deviation of prices around you. This is a very, very important feature for your quality score, but it's useless for actually having a price itself. But it's very good for imagining the range, how it might vary. So we are there, we created another new features for calculating, and we are back to quality score. And it works very well. Before running real model, we have quality score, how much we can trust it. We try to group those, and we see that really 20% of top reliable forecast is way better than compared to all the others. Okay, so the only point what has left, it goes again. A single house, this particular house, we have some kind of prediction. 3 million, 5, whatever, it's just a number. It pops out from our pipeline. And now here goes the questions like why this forecast is, and you can place any verb here. Why it is so high, why it is so low, can you explain this? And okay, no problem about that. I can run through all my pipeline, log all the differences, compare to it, and I will return to you with those questions for this particular house, but please don't come back with those questions ever again. Unfortunately, that's not how it works. Usually managers tend to come back with those kind of questions, and we need to prepare those answers. And this unlocks our final model, that storytelling model. So we need to find hints why it is so. So the approach goes like this, that we have a black box. We consider this current pipeline to be a black box. And we try to hit it by another black box and random forest. With naive approach, if you add two black boxes, it will eventually become a white box. This is a joke, but yeah, this is how we go. And the reason we chose this approach that random forest in classical terms was considered to be black box, but this is I have different opinion. Random forest is nothing but a bunch of decision trees. And by decision trees, you can actually access each and every decision tree that is in your random forest, go to each node, track each feature that was used to splitting this node, and forecast the shift of prediction in each node. After that, you can aggregate and have real contributions for each feature in your model. And this actually creates your hint, which features drive this forecast to one side or another side compared to something else. And this is how we go. We created another model that is slightly, well, it's not so good as our pipeline, but the forecasts are very correlated, and we're using those hints to tell a story about why this or that happened. And again, here, great question. Can we do any better? Now it's in a small size because I don't want to see it anymore. At some point we say, that's enough, this is our pipeline. Perhaps we can do it next year. Okay, and here we go, we are at the finish line. Happy days. Some lesson learned that I want to share with you that generalize my presentation. So 80-20 rule, that's sometimes referred as Pareto principle, that with 20% of efforts you can have 80% of result. That was valid in our case. So I'm not feeling good about it, but it's a law. And my supervisor told, well, you can't fight the laws. All you can do, try to collaborate with them. So we were in this. Neural networks are awesome. It's really awesome, and you can solve a lot of problems with it. But you need to use it wisely, otherwise you might end up spending a lot of time for the things that you are not going to use. Another thing is don't try to invent the wheel. If you have something that looks very similar, a module, a package of Python that pretty close, but not exactly what you need, try to have some workarounds to fit it. Otherwise, you also might find a lot of time of coding. Be aware of a black box at a time. That means please appreciate your managers. They're trying to do their thing, and sometimes it's very useful for all of us. And complexity grows very quickly. If you have each step is pretty simple, just index, another index, what's wrong with that? And at the end of the day, you have a huge pipeline, a giant beast that no one wants to touch it. So please aware of that if you're building something similar. And that's it from my side. It's time for questions. I was happy to be here. Please welcome.